Have you ever wondered what happens when a legendary brand, a name tied to the highest level of engineering for more than a century, suddenly disappears from every major conversation? Not because it failed, not because it gave up, but because it was quietly building something massive. That is exactly what happened to Rolls-Royce over the past several years. While Boeing and Airbus were fighting each other for global aircraft orders, while GE Aerospace was holding press conferences to show off thrust records, and while the entire aviation industry was drowning in the heavy aftermath of the pandemic, Rolls-Royce almost vanished. Thousands of workers were laid off, contracts were canceled, its stock price collapsed. Financial media outlets were already writing early obituaries for the brand. Everyone thought this was the sign of a company slowly fading away, and they were completely wrong, because while the world stopped paying attention to Rolls-Royce, that was exactly when the company began the boldest project in its 120-year history. Not a minor upgrade, not a concept drawing meant to impress people, but a fully working prototype, a machine that had already been tested in the real world and had passed every test with results so shocking that the aviation industry had to sit down and read the numbers again and again just to make sure they were real. They call it UltraFan, and that name was not chosen by accident. UltraFan is not just better than the previous generation of Rolls-Royce engines. It goes beyond almost everything commercial aviation has ever known. 25% better fuel efficiency, the largest fan ever fitted to a commercial aircraft engine, an advanced gearbox never before seen on an engine of this size. And most importantly, it has already been tested in real conditions with verifiable numbers, not just promises on paper. But here's where the story gets really interesting. UltraFan is not just a more powerful engine, it is a strategic statement, a direct strike at the future of the entire industry. A challenge aimed straight at GE, Boeing, and anyone who ever believed Rolls-Royce was finished. So, what is hidden inside this machine that makes it so special? Why are the world's biggest airlines watching every new move from Rolls-Royce so closely? And is this really the turning point that could completely reshape the aviation industry, or just another big promise from a brand trying to make a comeback? That is what we are going to find out in today's video. Before we get deep into this story, if you enjoy detailed analysis videos like this, make sure to subscribe right now so you do not miss what comes next. The aviation industry is standing at a crisis crossroads. To understand why UltraFan matters so much, we first need to look at the bigger picture. Commercial aviation is facing a double crisis unlike anything in its history. On one side, there is enormous economic pressure. Fuel can account for more than 30% of an airline's total operating costs. With each aircraft staying in service for decades, even 1% of fuel savings can create millions of dollars in difference every single year. Airlines do not simply want more efficient engines, they need them in order to survive. On the other side, environmental pressure is rising faster than ever. The European Union has been implementing the Fit for 55 program, a tough package of policies aimed at cutting carbon emissions by 55% by the year 2030. The International Civil Aviation Organization, or ICAO, is setting mandatory global emission limits. Some major airports in Europe and Japan have already started adding extra charges to flights that use older generation engines. This is no longer just a soft incentive. This is law. And airlines that fail to adapt will face both financial penalties and the risk of losing landing rights at some key airports. On top of that, there is another issue people talk about less, but it is becoming more important every year: noise. Communities living around airports in the United Kingdom, Germany, the Netherlands, Japan, and several U.S. states are pushing regulators to limit flight hours and flight numbers. Some airports have already imposed full nighttime flight bans. Louder aircraft mean fewer takeoff and landing slots, and fewer slots mean lower revenue. In short, the entire economic structure of aviation is being shaken from the ground up. Engine technology from the previous decade, no matter how efficient it looked by the standards of its time, is becoming less and less suited to this new reality. And this is the exact gap Rolls-Royce is targeting. But to understand why that matters so much, we need to look directly at the heart of the story, the machine everyone is talking about. What is UltraFan, and why are engineers so impressed by it? Rolls-Royce UltraFan is the result of 4 decades of accumulated research. But do not get it wrong. This is not just a step-by-step evolution of the earlier Trent family. This is a completely new design, built from the ground up with an entirely different philosophy. Let's start with the first thing you notice, the enormous fan at the front. UltraFan's fan has a diameter of 140 inches, about 3.56 meters. It is the largest fan ever built for a commercial aircraft engine in history. But size is not the only thing that makes it special. What really matters is how it is made. Each fan blade is made from carbon composite material, which is much lighter than titanium. But to survive impact, for example, if a bird accidentally flies into the engine at high speed, the leading edge of each blade is reinforced with titanium. The result is a blade that is light, strong, and flexible enough not to shatter when something unexpected happens. In aerospace engineering, this is what people call a win-win rare, but when it happens, it is worth paying attention to. Next comes the bypass ratio, a technical term, but an extremely important one. Imagine it this way. In a jet engine, not all the air passes through the engine core and gets burned. A large amount of air bypasses the core and creates thrust by being accelerated directly through the fan. That air is called bypass air. The higher the bypass ratio, the more efficient the engine becomes, and the quieter it usually is. UltraFan reaches a bypass ratio above 15:1. That number has never been seen before in a large commercial aircraft engine. For comparison, the best modern engines today are around 9:1 or 11:1. Rolls-Royce has pushed far beyond that limit. But the most impressive number in this entire story is not the fan size, and it is not the bypass ratio. It is 64 megawatts. That is the amount of power UltraFan's central gearbox successfully handled during testing. 64 megawatts through a single gearbox, a world record, recorded and verified under real-world conditions. To make that easier to understand, that is roughly equivalent to the power of 85,000 standard cars being pushed through a drivetrain about the size of a small truck. This gearbox is the soul of UltraFan. It allows the fan and the turbine to spin at their own optimal speeds instead of forcing both of them to rotate at one compromised speed. It is like the difference between a car with only one gear and a car with a multi-speed automatic transmission. Efficiency improves dramatically across all flight conditions. And finally, inside the engine core, where temperature and pressure reach the limits of physics, Rolls-Royce uses ceramic matrix composite material, also known as CMC. This material can withstand temperatures far beyond what traditional metal alloys can handle. That means the engine core can operate at higher temperatures, produce better thermal efficiency, and reduce fuel consumption even further. CMC is also lighter and more durable over time, which helps reduce maintenance frequency. None of this is just theory. It has been tested, it has been verified. UltraFan is a real working prototype, not just a demonstration model. At first, these may sound like interesting technical improvements, but the combination of all these technologies is what could change the entire game, and here is why. The real breakthrough is not technical, it is economic. When engineers talk about UltraFan, they talk about bypass ratio and CMC. But when airline executives sit in a boardroom and ask questions about UltraFan, they only want to know one thing. Is that number real? That number is 25%. UltraFan delivers 25% better fuel efficiency compared with the Trent XWB, currently the most efficient engine in Rolls-Royce's commercial portfolio and widely considered one of the most efficient engines in the world. This is not a comparison against an engine from 30 years ago. This is 25% better than one of the best engines available today. Now turn that number into money. An Airbus A350 flies about 3,500 hours per year on long-haul routes. Average fuel costs for this type of aircraft are around $15 to $20 million per year, depending on fuel prices and route structure. If UltraFan reduces that cost by 25%, that means a saving of around $3.75 million to $5 million per aircraft per year. A major airline operating 100 long-haul aircraft? Now we are talking about savings of up to $500 million a year from fuel alone, and that is only the starting point. Ultrafan's modular design means fewer exclusive components, shorter maintenance time, and lower spare parts inventory costs. Better control of operating temperatures means less wear and tear, extending the time between major overhauls. Built-in predictive analytics can detect potential problems before they become failures, reducing expensive unscheduled maintenance, reducing canceled flights, and reducing passenger compensation. Then comes carbon tax. The European Union has already started charging for carbon emissions from flights. An aircraft that burns less fuel produces fewer emissions, which means lower taxes. As this policy spreads and current trends strongly suggest more efficient engines will not just be a competitive advantage, they will become a survival requirement. And do not forget the noise factor. Airports like Amsterdam, London Heathrow, Frankfurt, and Tokyo Haneda are tightening noise restrictions. Louder aircraft lose nighttime slots. Losing nighttime slots means airlines cannot fully use the earning power of certain routes. Ultrafan, with the highest bypass ratio ever achieved and a low-speed fan design, is one of the quietest engines ever tested. That opens the door to more airports, more slots, and more revenue. When you look at the full picture, Ultrafan is not just an engineering achievement, it is a financial tool, a competitive weapon, and an insurance policy against increasingly strict regulations. Airlines understand this, and that is why the industry conversation is changing. But no matter how good a technology is, it cannot sell itself. And Rolls-Royce understands that if you want to change an industry, you need more than a superior product. You need the right alliances. Challenges and unanswered questions. At this point, if you think this story is just unlimited praise for Rolls-Royce, we need to stop and look at reality. Because Ultrafan is still facing serious challenges, and ignoring them would not be honest. The first challenge is time. Rolls-Royce announced the Ultrafan program back in 2014. The most recent prototype testing took place in 2023, but so far, no airline has signed a direct commercial order for Ultrafan. In aviation, the gap between a successful working prototype and mass production can take many years, sometimes a full decade. Airbus has worked with Rolls-Royce to integrate Ultrafan into future propulsion systems, but which aircraft will use it first is still not completely clear. The next-generation airframe, the aircraft designed from day one to take full advantage of the Ultrafan architecture, has not been finalized. That means the supply chain, production facilities, and FAA and EASA certification processes are still ahead. The second challenge is cost. CMC, carbon composite, a 64-megawatt gearbox. These materials and components are not cheap to produce at scale. The initial price of an Ultrafan engine will most likely be significantly higher than current options. For airlines still struggling to recover after the pandemic, the upfront investment is a real barrier, even if the long-term benefits are clear. The third challenge, and maybe the most subtle one, is industry inertia. Aviation is not a place that changes quickly. Every aircraft and engine purchasing decision is tied to maintenance contracts that can last 20 to 30 years. Airlines that have already invested in LEAP or GNX fleets have no immediate reason to switch, even if something better appears on the market. Change in aviation happens by aircraft generation, not by financial quarter. And finally, there's a question no one has answered completely. Is Ultrafan truly ready for large-scale production within this decade? Prototype testing is an achievement. Producing thousands of reliable engines at a competitive cost is a completely different challenge. Rolls-Royce understands all of this, and its answer is the alliance strategy we're about to talk about now. This is where the race becomes truly intense, because Rolls-Royce is not fighting alone, and its rivals are not standing still either. The engine war, GE9X, LEAP, and an order being overturned. To truly understand Ultrafan's position in the bigger picture, we need to look at its competitors. The strongest rival right now is the GE9X, an engine designed specifically for the Boeing 777X. The most impressive number behind the GE9X is thrust. 134,000 pounds of thrust, setting a world record. This is pure muscle, optimized for one purpose: pushing one of the world's largest aircraft into the sky with as much thrust as possible. But the GE9X has a structural problem that even GE cannot ignore. It is tied to a single aircraft. The 777X is the customer for the GE9X, and the 777X is years behind schedule. Commercial certification has been delayed again and again. Some airlines have cut back their orders. That means the GE9X, even though it is technically impressive, is tied to the fate of an aircraft program that is struggling. The second rival is the LEAP family, a partnership between GE and Safran, used on the Boeing 737 MAX and Airbus A320neo. LEAP is selling very well, with thousands of orders. But LEAP is an engine for the current generation, not the next one. It does not have a gearbox architecture like UltraFan, and it does not have the same ability to integrate with hydrogen or hybrid electric systems. This is where Rolls-Royce's strategy becomes sharp. In 2018, Rolls-Royce signed a partnership agreement with Airbus, co-funded by the European Union's Clean Sky 2 research program, a multi-billion euro initiative aimed at reducing aviation emissions. The goal was not simply to test UltraFan as a standalone engine, but to develop it as a complete integrated propulsion system where the engine, the mounting pylon, and the aerodynamic nacelle are designed together and optimized together instead of being developed separately. This is systems thinking, not just product thinking. And Airbus is betting on that for its next generation of aircraft. What Boeing does not have in this equation is worth noticing. While Airbus and Rolls-Royce are building a future architecture together, Boeing is still largely relying on traditional relationships with GE and a technology roadmap that has not been clearly defined. The 777X is delayed. The 737 MAX is still recovering from crisis, and the new midsize airplane project, also known as NMA, has been frozen indefinitely. But to be fair, GE is not sitting still. It is developing the CFM RISE engine family revolutionary innovation for sustainable engines, together with Safran, targeting a 20% efficiency improvement over LEAP. That program is also testing an open fan architecture, an even more radical design that could challenge UltraFan's fuel efficiency in the future. So this is not a simple two-sided race. It is a multi-dimensional competition, and no one can say for sure who will reach the next generation finish line first. So in the end, the biggest question remains. In such a fierce competitive landscape, does UltraFan have enough power to create real change, or is it just another name in an already crowded race? The future is being written by decisions made today. Now let's look ahead. Not next year, but 10 to 20 years from now. By 2035, analysts expect most major economies to have mandatory carbon pricing systems directly applied to aviation. In some regions, this is already happening. Once carbon costs become a fixed part of every airline's financial calculations, engines that burn less fuel are no longer just nice to have. They become necessary to protect profit margins. Sustainable aviation fuel, or SAF, is already being deployed, but it is still more expensive than conventional jet fuel. However, as SAF production scales up and costs come down, engines that are compatible with 100% SAF, like UltraFan is designed to be from the beginning, will become the natural choice. No major adjustment, no need for recertification. Further ahead is hydrogen. Airbus has announced its Zero-E program, targeting commercial hydrogen aircraft by the year 2035. Rolls-Royce, through UltraFan's modular architecture, has designed this system to be compatible with future hydrogen combustion. That does not mean UltraFan will fly on hydrogen tomorrow, but it does mean the architecture is ready to evolve when hydrogen storage technology becomes mature enough. And here's the deepest strategic point in the entire story. UltraFan is not just a product, it is a platform. Its modular architecture allows the same basic core to be adapted for different thrust levels, from narrow-body aircraft like the A320 family to wide-body aircraft like the A350 and future models. That means an airline could operate multiple aircraft types with the same technical system, the same maintenance team, and the same spare parts inventory. This is what fleet planners call fleet commonality, and it can save major airlines tens of millions of dollars every year. For consumers, the impact is not small either. Quieter and more efficient aircraft with lower operating costs eventually mean airlines can keep ticket prices more competitive as operating expenses rise. Long-haul routes to smaller airports, which used to be economically difficult, could become realistic with an engine this fuel efficient. For the entire industrial ecosystem, UltraFan sets a new benchmark. GE will have to accelerate CFM rise. Pratt & Whitney will have to rethink its GTF roadmap. Safran will have to find a way to close the modularity gap. The entire race will speed up, and in the end, that is good for everyone. Rolls-Royce is not just building an engine, it is building leverage to change the rules of the entire industry. Looking back at this whole story, one thing becomes clearer than ever. This is not a story about an aircraft engine. This is a story about what happens when an old and established organization decides not to compete under the old rules, but to sit down and rewrite the rules. Rolls-Royce, during the years when it seemed the quietest, did exactly that. It did not try to regain market share by making something slightly better than what already existed. It made a bet that the future of aviation would not be defined by who has the strongest engine, but by who has the most flexible, efficient, and sustainable ecosystem. And with UltraFan, that argument is starting to carry real weight. But, and this is important to remember, the future has not been fully written yet. UltraFan still needs full certification. Large-scale production is still an unknown. Airbus needs to decide exactly which aircraft will become the first home for this engine. GE is striking back with CFM Rise. And the market, as history has shown again and again, does not always reward the best technology. Sometimes it rewards the one that arrives at the right time, with the right partner, at exactly the right moment. Rolls-Royce is trying to be all three at once. So the final question, and maybe the most important one, is not, is UltraFan the best engine in the world? The technical numbers already give us a pretty clear answer to that. The real question is the aviation industry ready to change fast enough to embrace it? And over the next decade, the answer to that question could reshape everything from airline balance sheets to the ticket prices you pay, to the amount of carbon released into the atmosphere every time an aircraft leaves the runway. This is one of the most important races in modern industrial history, and it is happening right now, almost completely under the public radar. So, what do you think? Is UltraFan truly a turning point, or will aviation keep being held back by the inertia of old contracts and legacy systems? Rolls-Royce has already started the journey, but will it actually reach the finish line? Leave your thoughts in the comments below. And if this video made you see the aviation industry in a different way, do not forget to hit like and subscribe, because the story of this next generation engine still has many chapters ahead. Have you ever wondered what would happen if one night you woke up and everything you had always believed was untouchable in the global commercial aviation industry suddenly started falling apart? Not because of an accident, not because of a financial crisis, but because of one aircraft, an aircraft that much of the Western world once treated like a joke, had just completed a 12,000-kilometer journey without a single incident. That aircraft is China's C-929, and that test flight did not come with fireworks, a massive press conference, Hollywood celebrities, or some dramatic countdown. It was just one airplane taking off quietly and landing in a completely different world. For decades, people believed that the long-haul, wide-body aircraft market, the kind of aircraft that flies from New York to Tokyo, from Los Angeles to Dubai, belonged to only two giants, Boeing and Airbus. Nobody could touch that territory. The research costs were too massive, engine technology was too complicated, the international certification process was too long. But everything is changing, and it is changing much faster than most people expected. So what allowed a country that once depended almost completely on Western engines to design, build, and test fly a world-class long-range aircraft on its own? Is this really an existential threat to Boeing, or is it just a geopolitical show? And most importantly, if the C-929 receives commercial flight certification, what will the global aviation market look like? Let's find out together. But before we go deeper into this story, if you like honest analysis that does not dodge the truth about the global technology war, hit subscribe right now so you do not miss what comes next. How long has the monopoly over the sky been around? To understand why the C-929 is causing such a shock, you need to look back at history for a moment. Since the 1970s, the global commercial wide-body aircraft market has had only two real players, America's Boeing and Europe's Airbus. Every major airline in the world, from Delta, United and American Airlines to Emirates, Singapore Airlines, and Cathay Pacific, has had to choose between those two options. There was no third choice. And the reason is simple. Building a wide-body aircraft is not a normal engineering project. It requires tens of billions of dollars in research and development, advanced composite material technology, specialized engine systems, and most importantly, trust from international aviation certification agencies like the FAA in the United States or EASA in Europe. Even advanced economies like Japan have failed. Mitsubishi SpaceJet, a project that took decades and billions of dollars in investment, was finally canceled in 2023 without ever completing commercial certification. Canada's Bombardier had to sell its C-Series aircraft business to Airbus. Brazil's Embraer has only been able to focus on short-range and medium-range aircraft. Long-haul, wide-body aircraft that was untouchable territory. Or at least, that is what people used to think. The Boeing 787 Dreamliner and the Airbus A350 are the two symbols that dominate that segment. They can fly non-stop from the east coast of the United States to Asia, carry 250 to 350 passengers, burn up to 25% less fuel than the previous generation, and offer cabins comfortable enough for passengers to survive 14 to 16 hours in the air. But even those high points have cracks. Boeing is struggling with a production quality crisis. FAA investigations after the 737 MAX crashes and the Alaska Airlines door plug blowout incident in early 2024 threw both Boeing's brand and its supply chain into chaos. Deliveries slowed down, costs climbed, and customer trust started to fracture. That is the backdrop. And in that backdrop, China made its move. But to understand why this matters so much, we need to look at the core of the whole story, the story of how a broken alliance became the catalyst for one of the most ambitious aviation projects in history. The C-929 rose from the ashes of the CR-929. The year was 2016. While the world was watching Boeing roll out new 787 aircraft and Airbus expand its A350 production line, a signed document in Shanghai quietly laid the foundation for a revolution. China and Russia announced a partnership to develop a wide-body aircraft called the CR-929. On paper, it was a perfect alliance. Russia's United Aircraft Corporation, UAC, had decades of aerospace engineering experience. China's COMAC had massive industrial manufacturing scale and almost unlimited state funding. Both sides committed more than $2 billion in initial investment. The goal? Break the Boeing-Airbus monopoly in the long-haul aircraft segment. Fly non-stop from Beijing to London, from Moscow to Los Angeles. A true aircraft of the third world not dependent on Washington or Paris. The West paid attention. Boeing released an internal memo warning about threats from non-traditional players. Honeywell, GE, Safran Western Aviation suppliers quietly watched the project. Then, everything collapsed. In 2022, the war in Ukraine broke out. Western sanctions tightened around Russia like a noose. UAC was forced to focus its resources on military platforms. Key engineers were pulled away from the CR-929 project. Progress stalled. Emails went unanswered. Parts stopped arriving. But the real breaking point did not come from politics, it came from power. China wanted access to Russia's proprietary engine technology, including advanced high-pressure bypass fan designs. Russia refused. Intellectual property negotiations broke down. By the end of 2022, Russia pulled out of the project. The West breathed a sigh of relief. Aviation experts wrote obituaries for the CR-929, a victim of geopolitics, they said. Dead before it was born, aviation headlines declared. But nobody saw what was coming next. China did not bury the project. It renamed it. The CR-929 became the C-929, and instead of scaling back, COMAC accelerated. They hired more people, poured in more money, and started replacing foreign components one by one with domestic solutions. Avionics systems were swapped out, the fuselage design was rebuilt from the ground up, the certification process was restructured to align with international protocols through the Civil Aviation Administration of China, the CAAC. By the end of 2023, the first flight test model was ready. That may sound simple, but this small detail could change the entire game. China is not just building an aircraft, it is building a completely independent aviation ecosystem. What is inside the C929? That has the whole industry worried. This is not just a stretched-out C919. This is not a cheap copy of the Dreamliner. The C929 is a completely new wide-body design built to compete directly with the Boeing 787 and the Airbus A350, not just in size, but also in technology, passenger comfort, and total operating cost. Look at the numbers. The C929's wingspan stretches close to 65 meters longer than the Dreamliner. Its cabin is more than 5.5 meters wide, giving airlines flexibility in seating layouts, from 9 abreast economy seating to premium business class cabins optimized for long-haul routes. But size is not the biggest headline. The materials are what make the whole industry look twice. More than 50% of the C929's airframe is made from carbon fiber composite materials, a dramatic leap from Comac's earlier aircraft, and even slightly ahead of the A350. On top of that, about 15% titanium is used in key load-bearing areas. The result is an aircraft optimized for fuel efficiency, corrosion resistance, and durability on ultra-long-haul routes. Inside that shell, things get even more interesting. The C929 is expected to feature intelligent avionics with adaptive digital flight displays, ambient cockpit lighting to reduce pilot stress, and a real-time system monitoring suite similar to what the Boeing 787 pioneered, but rumored to include expanded diagnostic bandwidth across hydraulic, electrical, and thermal systems. Translated into business language, airlines could get predictive maintenance capability and reduced unplanned downtime, two of the most painful cost problems in modern fleets. Then comes the cabin, and here, Comac is not holding back. Designers have focused heavily on the passenger experience, integrating noise reduction materials, adaptive LED lighting, and modular seating options. Leaked drawings show larger windows, wider aisles, and an interior layout inspired by the minimalist design of the A350 combined with Embraer-style ergonomic seat spacing. And here is what makes all of this scary for Boeing and Airbus. This whole package of innovation is being offered at an estimated cost 15 to 20% lower than comparable Western products, especially for markets connected to the Belt and Road Initiative. This is not just an engineering win, it is an economic weapon. There's one more detail people do not talk about enough. Final assembly takes place inside the Shanghai Pilot-Free Trade Zone, a facility that is both a production line and a geopolitical firewall. The zone gives Comac tax exemptions, faster import and export clearance, and most importantly, full control over data and intellectual property. No Western company can simply walk in and observe. International oversight is minimal. The assembly line is embedded with Chinese-developed robotics rumored to include AI-assisted inspection systems that scan composite panels in real time for micro cracks and fatigue stress. Unlike Boeing's Everett factory, which depends heavily on legacy systems and layered outsourcing, Comac's production line is vertically integrated, fewer third parties, more in-house control. One engineer from the Shanghai Aircraft Design and Research Institute, speaking anonymously, described the philosophy clearly. We learned from the Dreamliner delays. Every failure Boeing suffered, we studied and adapted. But no matter how impressive the technology looks, it means nothing if it cannot be produced at scale and if it does not have the heart to fly on its own. What the C929 still has not proven. But let's slow down for a second, because this story would not be honest if it were all sunshine. The C929 still faces enormous challenges, and the biggest one is something China has struggled with for decades: engines. Let's be direct. Engines have always been China's weak point. The C919, the narrow-body aircraft that Comac spent more than 15 years perfecting, still depends on the LEAP-1C engine, a product co-developed by General Electric and Francis Safran. That is exactly the kind of dependence that allows the United States to control access, restrict exports, and even delay certification progress. With the C929, China's trying to break that grip through the CJ2000 engine, a next-generation turbofan being developed by the Aero Engine Corporation of China, or AECC. According to insiders at AECC, the CJ2000 is designed to deliver up to 35 tons of thrust, putting it directly in the performance class of the Rolls-Royce, Trent 1000, and GE GNX, both of which power the Boeing 787. On paper, the specifications sound impressive. A 3-meter fan diameter, an ultra-low bypass ratio for fuel savings, next-generation ceramic matrix composite materials to handle high turbine temperatures at a lower weight. But here is the reality. The CJ2000 is still in development. Bench testing has started. Early prototypes of fan blades and compressor stages are reportedly showing efficiency indicators within 10% of GE's newest models. But within 10% of the jet engine business is not success, it is the starting line. A 10% efficiency gap can translate into millions of dollars in operating costs every year for each aircraft. China's plan is to test the engine on the C929 in 2029, achieve full certification in 2031, and begin mass production in 2033. That is a very ambitious timeline, and history shows that new engines are often delayed by 3 to 5 years beyond the original plan. Then there is the international certification problem. Even if China's CAAC certifies the C929 for domestic flights, the question is whether the FAA and EASA will certify it for international operations. And if they do not, then the C929 can only fly on routes where Chinese regulators have influence, which basically means China's domestic market and Belt and Road-aligned countries. That still sounds like a huge market, and it is. But it is not the kind of global domination some claims are suggesting. And finally, there's the issue of passenger trust. The international aviation market does not buy aircraft based only on specifications. It buys based on safety records, after-sales service capability, and spare parts availability. COMAC has still not built a global service network that can compare with Boeing or Airbus. That is a massive commercial challenge that cannot be solved with state funding alone. And this is where the race becomes even more intense, because this company is not the only one trying to dominate the future of the sky. Boeing, Airbus, and the C929. Who is really where? Let's put these three aircraft side by side and look straight at the truth. The Boeing 787 Dreamliner is still the gold standard of the wide-body segment. It has a massive operating record, more than 1,000 aircraft in service around the world. Its after-sales service network reaches across 140 countries. Its systems integration technology has been proven through millions of commercial flight hours. But Boeing is struggling with problems nobody can deny. Production quality crises at the Renton and Everett plants, ongoing FAA investigations, and most importantly, a brand that has been badly damaged after the 737 MAX scandals. In the first quarter of 2024, Boeing delivered fewer than 80 aircraft, its lowest number in years. Airbus delivered more than 140 aircraft in the same period. The gap is widening. The Airbus A350 is seen as the smarter compromise. Excellent fuel efficiency, a spotless safety record, and Airbus's political flexibility as a European company less tied to United States-China trade disputes makes it more attractive to many airlines in emerging markets. But Airbus is not free from pressure either. Its supply chain is stretched, and it cannot ramp up production fast enough to meet post-pandemic demand recovery. So what does the C929 look like in that context? If China really delivers what it is promising, a long-range, wide-body aircraft with 50% composite materials, total lifecycle cost 20% lower, and built-in state-backed financing, then this is not just a competitor. This is a structural alternative, but here's the important balance point. The C929 and the Boeing 787 may never compete directly in the same market. Not because the C929 is not good enough, but because the two aircraft may serve two different ecosystems. Boeing continues to dominate North America, Western Europe, Japan, and South Korea markets where FAA and EASA standards are the gold standard. The C-929 could capture the rest of the world, Southeast Asia, South Asia, the Middle East, Africa, and Latin America, where infrastructure is still being built and purchasing decisions are less tied to Western geopolitics. And that is exactly what makes this competition not just an aircraft battle, but a systems war. Imagine this scenario. A developing country receives a loan from a Chinese state bank to build a new airport terminal. The construction is handled by a Chinese contractor. The radar and air traffic control systems come from Huawei's Aviation division. And when it is time to bring in aircraft to fill those new runways, the airplane parked on the tarmac is the C-929 purchased with Chinese state financing and bundled with below-market service packages. That is not just an aircraft purchase. That is the creation of a strategic partnership poured in concrete and steel. And once that infrastructure is built, it is very hard to reverse. Internal reports from Beijing's Ministry of Commerce show that at least 8 countries, including Pakistan, Kenya, and Malaysia, have expressed early interest in buying or leasing C-929 units once certification is complete. So in the end, the biggest question remains: is this technology truly powerful enough to change the future of the sky? Let's move to the next part. What will the aviation world look like over the next 10 years? This is the part everybody wants to know, but few people are willing to say out loud. Let's start with the most likely scenario over the next 5 years. If the CJ2000 falls behind schedule, which is entirely possible, based on the history of commercial jet engine development, then the C-929 will enter commercial service with a foreign or temporary engine, just like the C-919 is currently using the LEAP-1C. That would significantly limit China's claim of being fully independent and give the West important leverage, but it would not stop the launch. Even in that scenario, the C-929 could still create meaningful disruption in markets that do not require FAA certification. Southeast Asia, where ASEAN is one of the fastest-growing aviation markets in the world, could be the first battlefield. Looking further ahead to 2030 through 2035, if China executes its roadmap, the CJ2000 gets certified, the C-929 receives CAAC certification, and then begins seeking recognition from Asian and African regulators, the global picture will start changing in more fundamental ways. Boeing would see its market share shrink in the Asia-Pacific region. Airbus may hold its position in Europe and the Middle East thanks to diplomatic advantages, but it would still face pricing pressure. And airlines in emerging markets, which have long had to accept whatever Boeing or Airbus offered because there was no other real option, would suddenly have a genuine third choice. But the impact does not stop with aircraft. If the C-929 succeeds, it will create the next wave. The CJ2000 engine, if certified, would open the door to dozens of other applications. China's carbon fiber composite supply chain would grow to the point where it could compete with Japan's Toray and America's Hexcel, currently 2 of the largest aerospace composite material suppliers in the world. The accumulated knowledge from the C-929 would be applied to the next generation of aircraft. And here is the most important part for viewers watching from the United States. This competition does not just mean plane tickets might become cheaper. It means the balance of power in global aviation, an industry worth nearly $1 trillion, is starting to shift. And when aviation power shifts, it pulls commercial power, diplomatic influence, and ultimately geopolitics along with it. That is why a 12,000-kilometer test flight with no fireworks and no Hollywood-style launch matters more than any show. Because it is not a promise, it is proof, and proof changes everything. As for Boeing, the company is in one of the most difficult moments in its history. New CEO Kelly Ortberg is taking over a ship under pressure from every side: the FAA, airline customers, investors, and now a new competitor from the East. This is not a good moment to be weak while facing a strategic challenge on the scale of the C-929. One Western analyst summed it up very clearly. If the C-929 gets certified and reaches even moderate fuel efficiency, Boeing's dominance in the Asia-Pacific will end. Airbus has more diplomatic advantage, but even Airbus cannot compete with a $150 million aircraft that comes bundled with an airport upgrade package and 20-year financing. So where do we stand in this bigger story? The C-929 is not a silver bullet. It still has many challenges to overcome, the engine is not ready, international certification is uncertain, and the after-sales service network is not mature enough. Anyone who thinks Boeing and Airbus will collapse after one 12,000-kilometer test flight does not understand how the commercial aviation industry works. But this is clearer than ever. The race has begun, and this time, there is a real challenger. China has proven something many people once doubted, that a country can build a long-haul wide-body aircraft without Western permission. That changes the psychology of the entire industry. And in business, psychology often leads reality. The question is no longer whether the C-929 can fly. The question now is, who will sit on it, who will operate it, and who will shape the rules of the sky over the next 30 years? That is the question. Boeing, Airbus, Washington, Brussels, and Beijing are all trying to answer, and nobody is completely sure. What do you think? Is the C-929 really an existential threat to Boeing, or is it just an important geopolitical step that still is not enough to flip the whole game? Leave your thoughts in the comments below. And if this video gave you a new way to look at the technology war reshaping the world, hit like and subscribe, because this story is only just beginning to take off. For years, there was one question that Western aviation analysts always answered with confidence. No way. China could build its own aircraft carriers. It could develop stealth fighter jets. It could send people into space. But a next-generation jet engine for commercial airliners? Never. That was the final territory the West still had firmly under control, a field where, after decades of technological buildup, hundreds of thousands of test hours, and countless expensive failures, companies like CFM, Pratt & Whitney, and Rolls-Royce had built a wall that nobody could climb easily. But in early 2025, a technical report landed on the desks of analysts in Europe and the United States. And according to people familiar with the situation, the reaction inside companies like Boeing and Airbus was anything but calm. Because this was not some symbolic test. It was the clearest signal yet that China, through an engine called the CJ1000A, may be much further ahead than the world once believed. So, where does the CJ1000A really stand in this race? And if it succeeds, what could it change in the balance of power across the global aviation industry? To understand why this engine matters so much, you have to look back at the dangerous gap China has been forced to live with for years. China built the C-919, its first domestically developed narrow-body airliner and a direct rival to the Airbus, A320neo and Boeing 737 MAX. That alone was a major engineering achievement. But there was one detail Chinese officials were never comfortable talking about. Every C-919 flying today depends on the LEAP, 1C engine, a joint product of America's GE Aviation and France's Safran, a made-in-China airplane powered by a foreign heart. And the problem was never just national pride. The real issue is simple. Whoever controls the engine controls the entire program, and that has been proven in reality, not theory. In 2020, Washington considered blocking LEAP engine deliveries to China. Then, in 2025, the United States once again paused export approvals. The effect was almost immediate. No missiles, no sanctions package. Just one administrative decision. The C-919 assembly line had to slow down. Deliveries that airlines were waiting for suddenly stopped moving. COMAC's plan to deliver more than 30 aircraft that year was cut to just 25. 4 airlines that had already placed deposits had to push back their schedules. Pilots trained to fly the C-919 were left waiting because there were no new aircraft available for them. That pause only lasted a few weeks before approvals were restored in early July. But the real damage was not the number of delayed airplanes. It was the message the event sent. The C-919 might look ready for the world, but it could still be switched off with one phone call from Washington. With China expected to need more than 9,500 new aircraft over the next 20 years, that is not the kind of risk any long-term strategist can accept. That is why the CJ1000A is no longer just a long-term research project. After 2025, it became a critical part of China's entire civil aviation strategy. But to really understand this program, one thing needs to be clear. The road to the CJ1000A did not begin because of outside pressure. It began more than a decade ago, when engineers at AECC, the Aero Engine Corporation of China, were given the task of building something the country had never produced before. A high-bypass turbofan engine in the same class as the engines powering the A320neo and the 737 MAX. In 2011, a model of the CJ1000A appeared at the Beijing Air Show. At that point, it was mostly a statement of ambition. Then, in 2017, the first full demonstration engine was assembled. It was not built to fly yet. It was built to answer one question: could China's engine core reach the speed and temperature needed for commercial aviation? In 2018, the answer came. Inside a test facility in Shanghai, the CJ1000A reached full core speed for the first time. That was the moment the program moved from drawings and concepts into real hardware. But building an engine that can run and building an engine that is reliable enough for commercial service are two completely different things. The next stage, from 2019 to 2022, was the slowest and most brutal part of the process. Engineers pushed the engine through every extreme scenario they could think of. Temperatures as low as -40 degrees, heat above 50 degrees, sudden load changes, bird strikes, and mechanical vibration. Every test was not just about proving that the engine could survive. It was about finding every possible weakness that could destroy the entire program 5 years later. At the same time, COMAC prepared for a major step forward. The CJ1000A would be mounted on a Xi'an Y-20 heavy military transport aircraft, replacing one of its 4 standard engines. That gave engineers a way to collect real flight data without risking a passenger airliner. Basically, it turned the Y-20 into a flying test laboratory. By 2023, pictures started showing up on Chinese social media of a Y-20 flying with the CJ1000A, replacing one of its original engines. The program had entered the stage where most engine projects start exposing fatal weaknesses: overheating, instability, or microscopic cracks that cannot be seen until it is already too late. But reports from inside the program did not point to those problems. The engine reportedly handled full thrust without major issues. It responded cleanly to throttle changes. A former deputy director at COMAC, someone who had watched the C919 struggle through delay after delay, said the CJ1000A was exceeding his most optimistic expectations. In an industry where caution is almost instinctive, that is a remarkable thing to say. That does not mean the CJ1000A is ready, but what matters more is where it now sits in the development cycle. To get a realistic picture, put it next to the engines that currently dominate the narrow-body aircraft market. The LEAP 1C, the engine currently powering the C919, uses ceramic matrix composite materials, advanced composite fan blades, and cooling systems that allow it to operate at much higher temperatures, cutting fuel consumption significantly. In the efficiency race, the LEAP is still ahead. It has more flight hours, more data, and more years of refinement that China simply cannot compress overnight. But when it comes to thrust, the most important factor for replacing the current engine, the CJ1000A, has already reached the range needed for the C919. Its overall architecture is similar in size and class. It cannot beat the LEAP in efficiency yet, but it is capable of doing the job. Compared with Pratt & Whitney's PW1100G, the geared turbofan known for its strong efficiency but also infamous for early reliability issues, the CJ1000A has one unexpected advantage: simplicity. There is no complex gearbox. There is no risk of bearing wear that could force hundreds of aircraft to sit on the ground. Its early learning curve carries less risk. Of course, it also does not deliver the same efficiency level as the PW1100G, but that is not the goal. Many analysts place the CJ1000 closest to the later generation of the CFM56, not in terms of material standards, but in terms of technical maturity and potential reliability. The CFM56 is one of the most proven engines in aviation history. Comparing the CJ1000A to it is not casual praise. It is a sign that the Chinese engine may have moved beyond the danger zone that most engine projects never escape. And that is exactly where the tone among Western analysts is beginning to change. For years, the common assumption was that China would run into hidden problems that nobody could see yet. The kind of problems that only show up after thousands of accumulated flight hours and push a program back by several more years. But the latest test data suggests the opposite. The CJ1000A does not appear to be stuck in the early danger zone. It appears to be moving beyond it. The next question is no longer whether the engine can run. The question is, what does that change? If the CJ1000A receives commercial certification, something that still requires thousands of additional flight hours, teardown inspections after repeated operating cycles, and long-term durability testing, then the C919 becomes something completely different. It is no longer a made-in-China aircraft with a foreign heart. It becomes a complete product with an independent supply chain, protection from export pauses, and the ability to scale production at the pace Comac wants. Comac's long-term target of producing 100 to 200 aircraft per year no longer looks unrealistic, at least in the domestic market and in regions willing to accept Chinese certification. But the bigger impact does not stop there. A working CJ1000A means China can build its own independent maintenance and parts ecosystem, the same kind of ecosystem Boeing and Airbus use to establish their dominance for decades. Countries across Southeast Asia, the Middle East, Africa, and Central Asia could buy C919 aircraft with CJ1000A engines without depending on any Western supplier. No trade leverage. No geopolitical pressure from Washington or Brussels. For Boeing and Airbus, this is not an immediate threat. The C919 still needs years before it can receive EASA or FAA certification and enter the global market on a major scale. But the real concern is not today. It is the direction this is heading. If the first version is already this stable, then the second version will be better. The third will be more powerful. And by the fourth or fifth generation, the performance gap with the LEAP or the PW1100G, a gap that is still obvious today, could shrink to the point where it no longer matters commercially. This mechanism is not new. It is exactly what happened with container ships, solar panels, lithium batteries, smartphones, and electric vehicles. China does not need to win in the first round. It only needs to enter the ring and stay there long enough to learn, improve, and scale. Maybe the most important part of this entire story is not what the CJ1000A can do today, but what it is getting ready to unlock. The technical success of the CJ1000A does not erase Western leverage overnight. Bringing an engine from flight testing into commercial service still takes years. Chinese civil certification is one thing. Convincing airlines to trust that engine with hundreds of passengers on every flight is something else entirely. And the question of long-term durability data, the kind of problems that only appear after hundreds of thousands of operating hours, is still unknown. But all of that now speaks to timing, not technical possibility, and that is the real shift. For years, the Western aviation industry bet that China would never cross the technical threshold required to build a next-generation turbofan engine. The CJ1000A data is challenging that bet, not through some flashy launch event, not through a claim that it has beaten the LEAP, but through something much harder to argue with. Thousands of accumulated flight hours, stable performance, and steady progress. The latest test results do not create a headline saying, China has surpassed the West. They create something far more difficult to deal with. An engine core that is working, stable thrust, clean response, and flight hours stacking up in the right direction. Nobody can say for sure how long it will take for the CJ1000A to qualify for commercial service. But the more important question now is no longer, can China do it? It is this. When China finishes the current version and begins developing the next generation, which is likely already being built in secret, what will the aviation world look like then?